Swayam Prabha. Digital India. Educated India.
Welcome to Lecture 1, Refrigeration Principles, Part 2. Let us have a quick recap on what we have discussed in Part 1 under Lecture 1. We have seen the different types of processes like conventional cooling process, refrigeration, air conditioning, how each process differs from the history of refrigeration. And I have given an insight on star rated rating of refrigerator. We made a comparison on the energy, how much energy cost the electricity bill can be saved by making a comparison between 2-star rated refrigerator and 5-star rated refrigerator. Let us move to this part 2. So here, before seeing the fundamentals principles of refrigeration, there are a couple of terminologies which are used. One is source, another one is sink. How to define a source and a sink, or how does a source differs from sink? If you see this diagram, the left side, which is there, it is the source, and the right one is the sink. Source is a body with infinite heat capacity that supplies heat at constant temperature, and sink is a body with infinite heat capacity which absorbs heat at constant temperature. With this perspective, let us see what is the basis for the refrigeration principle, how does this refrigeration principle has evolved, and reversed Carnot cycle is the basis for the refrigeration principle. Before seeing the reversed Carnot cycle, let us see what is a Carnot cycle. What is a Carnot cycle? Let us see what is a Carnot cycle. So primarily it consists of two isothermal process and two reversible adiabatic process. Two, let me erase it. Yes or not? Two reversible adiabatic process. Reversible adiabatic process. Two isothermal and two reversible. So reversible adiabatic process is also called as isentropic process. Isothermal process is nothing but a process during which the temperature remains constant. All the four processes of a Carnot cycle are reversible processes. Two are isothermal and two are adiabatic, reversible adiabatic, which is also called as isentropic process. So this is the temperature entropy diagram. So let me write the heading as Carnot cycle. Carnot cycle. So this is process 1 to 2. This is process 1 to 2. That is isothermal expansion. And 2 to 3 is this one. Let me complete the process, then I will explain. So this is 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So from the thermal reservoir source, heat is supplied during the process 1 to 2. So this is Q1. Q1 is the amount of heat supplied by the heat source, which is a thermal reservoir. And since what happens during isothermal expansion processes, since the internal energy is zero, whatever the heat has been supplied, it is converted into useful work. It is converted into useful work since the change in internal energy is zero. So this is isothermal. 1 to 2 is isothermal expansion. 2 to 3 is reversible adiabatic process. Then 3 to 4, heat is rejected during process 3 to 4, heat is rejected, and 4 to 1 is reversible adiabatic. Let us plot the PV diagram. So this is entropy, this is temperature, pressure in the y-axis, and PV diagram. So this is process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So this is during process 1 to 2, Q1 is the amount of heat supplied, and during 3 to 4, Q2 is the amount of heat rejected. So if you see 2 to 3 is isentropic process. I said there are 2 isothermal process and 2 isentropic process. So if you see 1 to 2 and 3 to 4, both are isothermal process, and 2 to 3 and 4 to 1 are reversible adiabatic process. Reversible adiabatic process. And if you see the PV diagram, 1 to 2 is isothermal expansion, 2 to 3 is reversible adiabatic expansion, 3 to 4 is isothermal compression, and 4 to 1 is reversible adiabatic compression. So 2 compression and 2 expansion process, a combination of isothermal and reversible adiabatic. The other name for reversible adiabatic process, isentropic process. So here, if you say, this is the basis, Carnot cycle is the basis for any engine. This is a reference cycle to compare the performance for comparison of compare the performance with that of any engine. When we come to refrigeration cycle, the reversed Carnot cycle is the basis for comparison of the performance of a refrigerator or a heat pump So let me again repeat, the Carnot cycle is the reference cycle or the base cycle for comparing the performance of the engine which is operating between a source and a sink, and reversed Carnot cycle forms the basis for the principles of refrigeration, and where we can compare the performance of a refrigerator heat pump with that of a reversed Carnot cycle. If you see the name, there is a term called reversed. So what happens when we reverse the processes of a Carnot cycle? It becomes reversed Carnot cycle. that is by changing the direction of the processes. So what happens is, if you see the Carnot cycle, the arrow mark is in the clockwise direction. The arrow marks of various processes are in a clockwise direction. But if you see the reverse Carnot cycle, which is the basis for the refrigeration cycle, the arrow marks are in the anti-clockwise direction. So reverse, I change the direction of the processes of a Carnot cycle, it becomes a reversed Carnot cycle. So here, before seeing the reverse Carnot cycle, if we evaluate the efficiency of this Carnot heat engine, which is operating between two temperature limits, T1 and T2. Okay, so this is temperature T1, which is equal to T2, because it is an isothermal process, and this is temperature T3 is equal to T4. T3 is equal to T4. And if you see the efficiency of Carnot heat engine, efficiency is output by input. So if you calculate, Q1 is the heat supplied and Q2 is the heat rejected, divided by heat supplied. So if you divide, or in terms of temperature also we can write T1 minus T2 by T1. So if you divide, you will get 1 minus T2 by T1. And if you see the efficiency term, it contains two temperature limit, T2 and T1. So the efficiency of a Carnot engine depends upon the temperature of the source as well as the temperature of the sink. Suppose if T2 is not there, then that ratio becomes 0. Efficiency is equal to 1 minus 0 is 1, which is 100%. So it is difficult, it is not possible to operate a heat engine with a single reservoir. So it violates the second law of thermodynamics, which is the Kelvin-Planck state. For an engine to operate, there should be two reservoirs. One is called source, the other one is called as a sink. Now let us move to the reverse Carnot cycle. It consists of 4 processes again. So here if you see, process 1 to 2 is compression, which takes place in a compressor. 2 to 3, I have used the term, I mean, the component is the condenser, where the phase change process takes place. 3 to 4 is turbine expansion, and 4 to 1 is evaporator. So there is one small correction here, because in the next slide I have used term 1, 2, 3, 4. So similarly here I have used QL and QH. L and H terminologies, the suffix I will change it. Just a small correction. So here QL is nothing but Q1, and QH is nothing but Q2. So this is a small type topographical error is there. Okay. So Q1 and Q2. So if you see the reverse Carnot cycle, in case of a Carnot cycle, the heat is transferred from a high temperature body to a low temperature. Okay. Heat is supplied by the thermal reservoir source. The engine does work, and the remaining heat is rejected to the sink. Whereas in case of a reverse Carnot cycle, if we want to transfer heat from a low temperature region to a high temperature region, it is possible only at the expense of some external work. Without doing any external work or without using a power absorbing device like a compressor, it is not possible to transfer the heat from a low temperature region to the high temperature region. This is what Clausius statement of second law of thermodynamics states that. So here let us go to the diagram. This is the TS diagram of a reversed Carnot cycle. Of course, this is not the actual refrigeration diagram. There will be the Carnot cycle and the reverse Carnot cycle both are ideal cycle. So if we compare with the actual cycles, there will be deviation. So here this is 1 to 2. If you see the diagram here, 1 to 2 is compression. So assuming since it's an ideal cycle, 1 to 2 is isentropic compression. Process 1 to 2 is isentropic compression. 2 to 3 is constant temperature or isothermal. If we compare the diagram, it is heat rejection process. Heat is rejected. And 3 to 4 is reversible adiabatic or isentropic expansion. And 4 to 1 is isothermal heat addition. Let me repeat. Process 1 to 2 is isentropic compression. 2 to 3 is heat rejection process, isothermal. 3 to 4 is isentropic expansion, and 4 to 1 is isothermal heat addition process. So if you see, there are two isothermal process, and two isentropic processes. The COP of a reversed Carnot cycle is expressed as T1 divided by T2 minus T1. T1 divided by T2 minus T1. So, two isothermal and two isentropic process. The other name for isentropic is reversible adiabatic. So, if I want to evaluate the COP of a heat pump, in the next slide I will explain the difference between a heat pump and a refrigerator. So, at that time you will be able to understand. So, this is the schematic of a refrigerator and a heat pump. So, here you can see heat is transferred from a low temperature region T1 to a high temperature region T2. T1 to T2. So, initially I have used the suffixes L and H, which has been changed in the previous diagram. So, I have changed it here also. Now, refrigerator, this is a heat pump. If you see this one, in case of a refrigerator, the desired output, COP is the coefficient of performance, which is the ratio of desired output to the power required to drive a compressor in the actual cycle. So here the desired output, if you see the desired output, in case of refrigerator, my focus is how much heat is removed from the low temperature region. And in case of heat pump, I am not bothered about the amount of heat which is removed from this low temperature region. Rather, my focus is how much heat is rejected. So if you go to the previous one, the COP of the reversed Carnot cycle, it is mentioned as T1 divided by T2 minus T1. So, in case of a refrigerator, my desired output is Q1, and in case of this, Q1 is the amount of heat which is from the thermal reservoir T1, and in case of heat pump, my desired output is how much heat is rejected to the thermal reservoir. So that is the only difference. Otherwise, if you see the W net, it is the difference between Q2 and Q1. It is the difference between Q2 and Q1 in case of both refrigerator and heat pump. There is no change in the denominator. Only the numerator, the desired output will change. Let us see the limitations of the Carnot cycle. What are all the limitations? If you see the Carnot cycle, there are all the processes are reversible, two isothermal and two isentropic process. Achieving these processes in practice is very, very challenging. It is not possible. It is impossible, because if you take any processes, any thermodynamic processes in real time application, they are all irreversible. They are all irreversible in the sense they cannot be reversed perfectly. They cannot be reversed perfectly. And second point is, isothermal process requires a very slow speed of operation, and it is difficult to achieve, especially when we are using the compressor in the case of a vapor compression refrigeration system. So the speed of the compressor, when we say the slow speed is required, it is not easy to achieve that condition in reality. Compression and expansion should be at a very high speed. So here again, for isothermal process, the speed has to be low, and for the compression and of course, though the isothermal process, heat rejection and heat addition, not compression process. Compression process next one. So when we say isothermal process require a very slow speed of operation, that is the heat rejection and the heat addition process. Process 223 and 421. Process 223 and these two processes. 223 and 421. These two are isothermal process. So the next, when we compression process, which is 1 to 2, and expansion process should be at very high speed. Hence, in a single cycle, maintaining both high and low speed is not possible. Apart from these, there are limitations also, like in the actual cycle, there will be losses due to friction. Friction will be there in practice. There will be heat loss, irreversibilities. So achieving the Carnot cycle, achieving a Carnot cycle in real-time processes not possible. Before we conclude the part 2, let us define the units of refrigeration. It is expressed as 1 TR, 1 tons of refrigeration. It is the amount of heat required to be removed from amount of heat required to be removed from 1 ton of water at 0 degrees centigrade in a day. Like we have 1 ton of water, which is 1000 kg. How much quantity of heat is required to be removed in order to convert the water into ice in a time period of 1 day. So 1 ton of refrigeration I have given in different units. In SI unit, it is 210 kilojoule per minute. In MKS unit, it is 50 calories per minute. 1 calorie is 4.18 joule. So if you multiply 4.18 by 50 calories, kilocalories by 4.18, you will get around 210 kilojoules per minute. And in terms of British thermal unit per hour, BTU, that is British system, it is 12,000 BTU per hour. 12,000 BTU per hour. So here, if you see, 1 ton of 1 kilocalorie is equal to 4.18 kilojoules. So 50 kilocalories will be equal to 210 kilojoules, okay, of course, per minute. Coefficient of performance, it is the ratio of refrigerating effect to the energy spent. Now, what is the refrigerant? It is the amount of heat removed from the substance. Like I was explaining, in case of refrigerator, the desired output is Q1. How much heat is, my desired focus is this one. This is the diagram. Q1 is the desired output. How much heat is removed from the body or from the medium. In case of heat pump, how much heat is rejected to the thermal reservoir. That is the desired effect. So now, in this ratio, the numerator is the refrigerating effect, because we are this is since the subject name is refrigeration cold chain management, we will be evaluating the COP of refrigerator and not heat pump. Energy spent. There are two types of this one. One is it is in the form of work. So in case of a vapor compression system, how much electrical energy has been used to achieve this process? And in case of vapor absorption system, which is a heat operated system, which requires very minimal energy to operate a pump and the fan, which does not have a compressor. So it is called a heat operated system. So since in the first module and the second module, we will be studying about the vapor compression system. So the COP formula will be refrigerating effect divided by work done by the compressor. Work done on the compressor. That is how much energy is used to drive the compressor. So just to see how these values have come, and in terms of kilowatt, if you see 1 ton of refrigeration, 1 TR is equal to 3.52 kilowatts. 3.52 kilowatt. 1 ton of refrigeration is equal to 3.52 kilowatt. So how we got this one? Let me explain this one quickly. The 1 ton of ice is 1000 kg. 1 ton of ice is 1000 kg. Latent heat of fusion of ice 335 kilojoule per kg. The time period is 24 hours. If you 24 hours. 24 into 3600 seconds. So as per the definition of ton of refrigeration, heat required to convert the water at 0 centigrade into ice in 24 hours. So I have divided by that 3600 seconds. So here if you do, you will get around 3.8 kilowatt. This is actual 1 TR. So for people from the industry started using, instead of taking 3.8, and 1 ton of refrigeration is taken as around 3.5 kilowatt for practical purposes and for calculation. So with this, let me conclude the part 2. Thank you.